All right, let's go ahead and start looking at the warm-up problem. So problem number 1, you need to find the zeros. So the key for finding the zeros is you set the equation equal to 0, and then you're solving for x. And that's exactly what we do with problem number 2 as well. We set it equal to 0 to find the zeros. And for this problem, we need to factor it because it's a quadratic function. So I see a positive 10, so it's going to be two negative numbers, and they need to add up to 7. So I think it's 5 and 2 is going to get me that negative 7x. And then I would need to solve for each one individually. So I'd start with x minus 2 equals 0, and I get x equals 2. That's one of my x-intercepts. X minus 5 equals 0. I add 5 to both sides. I get x equals 5. That's the other x-intercept. And then I should be able to just go to Desmos and sketch a quick graph. But I just want to verify that those are my x-intercepts when I graph it. I'll get something that looks like this. That's what we're doing for problems 1 and 2. So we're finding the zeros algebraically. We're verifying them by graphing. Problems 3 through 8. I just want to be able to rewrite each of these in factored form. Because I have a minus 16 here and a subtraction problem, this we might remember from last year is called a difference of squares, which you should have talked about in AGS3 last year. And that means you take the square root of 16 and you'll end up with like an x plus and an x minus equation. That's going to be x plus the square root of 16 and x minus the square root of 16. And the square root of 16 happens to be 4. So that's x plus 4, x minus 4. That's factored form. Okay, we might also call it intercept form because it helps you identify those x-intercepts. That's why we called it factored form or intercept form. Okay, for problem 4, x squared plus 7x plus 10. If I need to, I can draw the area model, like do the box method. On this one, it looks very similar to what I had up above, except it was minus 7x instead. So it should be x plus 5 and x plus 2. Problem 5 is another difference of squares problem, except this time I would have to square root 5, and there's no way to easily square root 5, so I can just leave it in factored form as x plus square root of 5, x minus square root of 5. Problem 6, all right, I'm going to go ahead and I'll set up my box method to try it out. X squared plus 6x minus 7, just so you guys can see one that looks like this. The possible factors of 7 are 7 and 1. So if I started with like a minus 7 and a plus 1, I'm going to get minus 7x here plus 1x, and that would give me a negative 6x in the middle. So that's not going to work. So I'm going to probably want to switch the signs. And I can do a minus 1 and a plus 7. That gives me a positive 7x. And a minus 1x in there. And that gives me a positive 6x. So my factored form would be x plus 7 and x minus 1. That's how I use the box method to do it. And I think the box method is going to be good for these last 3 problems, or these last 2 problems especially, because I have a 2x and a 3x. I think it's a little easier to see because I know that this one's going to be 2x times x. This one over here with a 3x squared plus 5x plus 2. I know this is going to be a 3x times x gives me that 3x squared. The possible factors of 4, you could do 1 and 4. It's like 2x minus 1 and x plus 4, something like that. Or you can do 2 and 2. And if I did 1 and 4 first, I'm going to get negative 1x and positive 8x. And that's going to be just slightly wrong. I need a negative 7x. So I'm on the right track though. So I need it to be a negative 8x instead. And remember, it's 8 because it's 4 times 2. That's where the 8 comes from. So I need this to be an x minus 4 and an 2x plus 1. And that'll give me the right values there. So this problem comes out to 2x plus 1 and x minus 4. Last problem, the only factors of 2 are 1 and 2. And because it's plus and plus, I think they're both going to be plus here. So I do a 6x squared, positive 6x squared, and a positive 1x. That gives me a positive 7x. So that won't work. So I'll need to probably switch the 1 and the 2. And I can do a 3x plus 1 and an x plus, oops, I already did the 3x plus 1. I'm going to do the 3x plus 2 and the x plus 1, and that gets me a 3x here and a 2x there, and that gets me my 5x. So I just kind of play around with it until I get it right. And that's how I ended up with my values for this problem. Being able to simplify is very important, and rewrite these things in factored form. Super important to be successful in what we're going to be talking about next. Which today we're going to be talking about the remainder theorem. That's the big thing. So this topic today is called applying the remainder. Today's the second. So if we start, we have a polynomial f of x. It's divided by x minus k. So there's our divisor. Then the meaning of the remainder is this. F of k equals r. All right, that would be our remainder. Another way to write this would say our quotient of x plus our remainder over x minus k. All right. Well, actually, that would be our solution, right? This would equal f of x. All right, that's what this equation kind of looks like when we're done. We have our quotient plus our remainder. That's what we practiced the last few class periods when we simplified these division problems. Now, if the remainder was 0, then what happens is we would end up with 0 over x minus k. So it'd be our quotient of x plus 0 over x minus k, or just our quotient of x. We would just have the quotient left. All right. So that's what's happening if we have a remainder of 0. All right. When I tell you that a polynomial has a factor, definitely has a factor, that means it's going to have a remainder of 0. All right. So we want to make a quick note of that. We're going to have a remainder must equal 0 if we are given a factor. All right. Okay, that's the idea here. So a polynomial f of x has a factor if and only if this is true. Though we find that value k and it equals 0, that'd be it. Okay, now that's all kind of weird, but what we really want to focus on here is once we prove a remainder equals 0, whoops. Once we prove a remainder of 0, we want to factor the entire equation as well. All right, and what I mean by that is we want to try and rewrite our solution in factored form. That's the goal here. So what I mean by that is we say f of x equals like, we'll say x plus 1, x plus 2. That's what factored form of a quadratic function looks like, degree 2. Okay, and we know it's a degree 2 because there are two x's in it when it's in factored form, x plus 1 and x plus 2. A cubic function, f of x equals, I'm just making these numbers up by the way, x plus 1 plus x plus 2 times x minus 3, something weird like that. That'd be an example of a cubic function where I have 3 x's in the degree of the polynomial. A quartic function could have 4 x's, and it's going to look something like this. And it's going to be x plus 1, x plus 2, x minus 3, and then something weird like 2x minus 3. I don't know, just something random like that. That'd be a good example of a quartic function. And there should be 4 x's in the equation. That's how I know it's a 4th degree polynomial. So when we're in standard form, we can tell it's a 4th degree polynomial because the highest degree number will be x to the 4th power. But when it's in factored form, we know it's going to be a degree 4 polynomial because there are 4 x's written down in factored form. And just a quick note, remember that factored form also means intercept form. Remember, we want to put these equations into factored form so that way we can identify the x-intercepts easily. All right, that's the whole idea here. That's why we want to go to factored form. Okay. Now there's some important vocabulary we got to know. For example, if we are given one factor of a polynomial, we might be asked to find the other factors. All right, and a factor might look like x minus 4. That's a factor. All right, just an example of what a factor looks like. Example 1 below will be an example of factored form as well. All right, something else that might happen if we're given 1, 0, find the other zeros. All right, so it's like x equals 4 is an example of a 0. Okay, so you can see how it's kind of related to the x minus 4. That's where we would solve for both sides. Remember we said to find a 0, you set the equation equal to 0. X minus 4 equals 0. Add 4 to both sides, you get x equals 4. And now you've got yourself a 0. So we might use that word zeros as well. The last one we might use is this word solution. Given one solution of a polynomial, find the other solutions. And a solution is going to look like this. F of 4 equals 0. Okay, so those are important vocabulary words. They all mean something slightly different. The notation is just a little bit different for each one, but they're all the same general idea, right? Factored form is so I can write it a quadratic in a different form of the equation. A 0 helps me identify the x-intercepts, and then a solution is just kind of putting it all together. All right, so when I say what is a 0, it's essentially an x-intercept. That's what it is. But just remember that we have those different forms, right? So we have the factor, which would be like an example is x minus 1. The 0 of this would be x equals 1. The solution would be f of 1 equals 0. And then if we wanted to write an x-intercept, the x-intercept for this one would be 1, 0. So you can see that they're written slightly differently, but they all mean pretty much the same thing, right? We see that same theme. We have to know how to identify each type of problem here. Okay. Any questions before we take a look at our first examples of the day? That's kind of a lot of lecture all at once there. But we're going to break it down, and if it doesn't make sense to you yet, hopefully it does make sense when we start looking at the examples here. So problem number 1 says factor. So it says when I'm given this problem, when 2x minus 1 is a factor, that's a huge hint for me. That tells me we're going to have a remainder of 0. All right. So what we're going to do is we're going to do polynomial long division for this problem. We'll start by saying, okay, we have a third degree polynomial. There should be 4 terms. 2x cubed plus x squared minus 41x plus 20. 1, 2, 3, 4 terms. Perfect. All right. I'm going to need to use polynomial long division here, not that synthetic division that we did last time. And the reason is right here. I have a 2x. Remember we said that synthetic division doesn't seem to really work when we have a number other than 1 in front of that x. So I've got this 2x cubed. I want to get it 2x cubed below it so I can subtract eventually. So I have to multiply something by 2x, and that's going to be x squared. And now I can multiply that x squared by 2x. That gives me 2x cubed, and x squared times 1 gets me, or times negative 1 gets me a negative x squared. And then the most important part, don't forget to distribute that negative through to all of the terms. So this becomes a negative 2x cubed plus x squared. So then I get a 2x squared minus 41x. And now I have to multiply by 2 again. This is going to be 2x times x equals 2x squared. X times 2x is 2x squared. X times negative 1 is negative x. And then I have to distribute and change all of the signs. I want that 2x squared minus 2x squared to go away. And this becomes a plus x over here. So now I have negative 41x plus x gets me negative 40x. And then I have plus 20. And now I have 2x times something equals negative 40x. So it should be negative 20. And 2x times negative 20 times negative 1 is a positive 20. And at the last step here, when I'm distributing this negative, I should hopefully end up with a 0. And I think I do. I get a plus and a minus. And sure enough, yeah, I end up getting a remainder of 0, which is perfect because I'm supposed to have a remainder of 0. So that's good. That's a really good thing. And now what it says here, it says we're going to use long division to break down the cubic function, and then we're going to factor the resulting quadratic equation before finally comparing our results to the x-intercept on the graph. So we started with this equation, 2x cubed plus x squared minus 41x plus 20. After we factored, we know that 2x minus 1 is a factor. We're left with this x squared plus x minus 20. So we use polynomial long division to factor the equation, break it down a little bit. And I still have this x squared plus x minus 20. And I want to be able to break that down as well. And I can see if I can factor it. And say, okay, so I got a minus 20 there, so I can say x plus 5, x minus 4, because they should be 1 digit apart. And I get a minus 4x, a positive 5x. And yes, that works. That's perfect. So my final answer should be 2x minus 1 times x plus 5 times x minus 4. And the whole idea is I'm trying to write this thing in factored form. So that last part was simply just saying, let's factor this equation here. I had this, and that's what I put down in the diagonals. And then I tried to factor it, so I came up with x minus 4 and x plus 5, and that's what I put here. Okay, the order doesn't matter as long as I have three binomials being multiplied. Another key that I want to point out here real quick, this started as x to the third power in standard form. Then I have 1, 2, 3 x's when I got down to factored form. That's what this should look like when it's all said and done. And the last part I say was compare our results by graphing. So what I want to do is I want to actually pull this up on Desmos and look at my graphs for these problems. So I'm going to share my screen with you guys. Up. And what I want to do is I want to start by graphing the original equation, 2x cubed plus x squared minus 41x plus 20. And technically I can graph the intermediate equation too, which after I divided, I had 2x minus 1 times x squared plus x minus 20. And if you guys notice, it's the exact same equation, or it's the exact same graph. That's a good thing. That means I did the division correctly. So not only did I have a remainder of 0, but when I graph it, the graphs line up. They overlay on top of each other. That's perfect. When I do the factored form, I should also get the exact same equation. It's like I'm checking my answer here by graphing it on Desmos. And sure enough, look at that, exact same equation again. So I have the red one and the green one on top of each other. So that means I factored this correctly. And I should be able to see, like, hey, I have an x plus 5, so there should be a negative 5 as next intercept. And there it is, negative 5 comma 0. There should be a positive 4 comma 0 as next intercept, and there it is. And then 2x minus 1 is going to be a positive 1/2 if I went ahead and solved for the zeros there. So that's how I can verify that I did this correctly. I should have the 3 zeros on my graph. Okay, so this problem, example 1, asked us to end with a factored form equation. So my solution here is this factored form equation, 2x minus 1 times x plus 5 times x minus 4. All right, that's example 1. That's what this looks like. All right. Example 2 is going to show us where the vocabulary needs to happen. So 1 0 is x equals negative 2. What are the other zeros? So I need to find the other zeros of f. And in this example, we can do synthetic division instead of polynomial long division. One of the things I like about synthetic division is you can use zeros for synthetic division. You have to use factors for polynomial long division. So since we already have the 0, I'm set to go. I have a degree 3 polynomial, so I should have 4 coefficients. And I have 1, 2, 3, 4 coefficients here. The 1, the 2, the negative 9, and the negative 18. We practiced a lot of this synthetic division on the assignment, so hopefully it's easy for us now. I do 1 times negative 2, I get negative 2, I get a 0 there, I get another 0 there, negative 9, positive 18, and a 0. Perfect, I had a remainder of 0. That's what I want to see, remainder 0. Now, the next step here is I'm going to write down my original equation. This is what this function started as. And now I'm going to write down the factored form. So I had x equals negative 2. I need to add 2 to both sides to get my factor. X plus 2 equals 0. So the factor was x plus 2. And I ended up with an x squared plus 0x minus 9. So it's just x squared minus 9 over here. And now I need to factor that x squared minus 9. That's the last part here. I get this x plus 2, x plus 3, and x minus 3 because it's a difference of squares problem. There's no middle value, so I should just be able to do the square root of 9. X plus the square root of 9, x minus the square root of 9. And in this case, that's 3 and negative 3. So now I've got factored form written down. But this question's asking, what are the other zeros? So I would actually need to solve for them. X plus 3 equals 0. Subtract 3 from both sides, I get x equals negative 3. X minus 3 equals 0. I add 3 to both sides, and I get x equals positive 3. So my zeros in this equation are negative 3, negative 2, and 3. Always make sure you're answering what the question is asking of you. So in this case, it says, what are the zeros? So I want to answer what the zeros are. In the first one, it asked, what are the factors? So I found the factors. It's never a bad idea to get in the habit of writing both factored form and the zeros down. Because if I do that, then if I forget to answer one part of the question, if I forget to answer what are the zeros, but I'm in the habit of writing them down anyway, then I won't get marked wrong on a test for writing down factored form when I was asked what are the zeros. So it's not a bad thing to be in that habit. Okay. And now with example 2, I should be able to graph this one and verify it as well. So I can go back to the equation, x cubed plus 2x squared minus 9 minus 18. And I should be able to see on this graph, oops, 2x squared minus 9x, there we go. I should be able to see on this graph, I should be able to see 3 zeros. I got one at an intercept at negative 3 comma 0. That's one of my zeros, is negative 3. I got an intercept at negative 2 comma 0. That was the 0 that was given, the negative 2. And I got an intercept at 3 comma 0, so that's the last 0. So there they are, negative 3, negative 2, and 3. I don't even need to graph my equation. I'm so confident I got this correct. But I can graph it anyway just to make sure. So I can graph x plus 2, x plus 3, x minus 3. And there it is. Perfect. Lines up perfectly, so that means I did this equation correctly. All right. So I have factored form, and I know what my zeros are. Desmos is going to be very handy for helping us check our answers, okay? I still need to show my work algebraically, but Desmos is a great way to verify that I did the question correctly. You should be able to have every single answer on the next test. All the answers are given to you, but you got to be able to show your work algebraically to prove that you're doing it correctly. All right? The last one, example 3, before I switch back to my iPad, it says find all of the zeros, and it doesn't give me any zeros. It just gives me an equation, 2x cubed minus 5x squared minus 4x plus 7. So I'm going to start by graphing that equation. 2x cubed minus 5x squared minus 4x plus 7. And I'm graphing it because this one says, without a 0 to start with, I want to use the graph to find a 0, and then I can simplify it from there. So I'm looking at my 3 zeros here. I have this negative 1.266, a 1, and a 2.766. And now I'm going to want to do division for these. So I'm going to want to use one of these zeros for division. And me personally, I think the 1's going to be the easiest one to use, the 1 comma 0 x-intercept. But what I want to do is on my other paper, before I go back to it, I'm going to write down what my zeros are. They're approximations, they're not exact, but that's okay. I have the negative 1.266, the 1, and the 2.766. And now I'm going to go back to my other screen. All right, so we should be able to see my screen again. I want to use that 1 as my 0 here. And it's a third degree polynomial. I should have 4 terms. And I do, so I don't need any 0 placeholders. That's nice. And now I'm just going to go ahead and do my polynomial division here, or my synthetic division. -3 times 1 is -3. I got -7 there, -7, and I got a 0. Perfect. I should have a remainder of 0. So this equation started as 2x cubed minus 5x squared minus 4x plus 7. Now, it's been factored once, and because it was an x, or x equals 1 was my 0, it's going to be a factor of x minus 1, and I'm left with 2x squared minus 3x minus 7. And I can go ahead and see about factoring that now. I can set up my box method. 2x squared minus 3x minus 7. The nice thing is that 2 and 7 are both prime numbers. So I know this is going to be like 2x and x, and then I can do 1 and 7 here, or 7 and 1 the other way. And one of these is going to need to be positive, one's going to need to be negative. The bigger one will need to be a negative. So I get negative 7x and positive 2x. Well, that only gives me negative 5x. Not negative 3x. And so that means this factor method is not going to work. And that kind of makes sense too, because if I was looking at the graph, I saw negative 1.266 and 2.766. So it's not going to give me nice integer values when I'm trying to factor it. All right. So what I'm going to need to do then is I'm going to need to use the quadratic formula for this problem. So more throwback to AGS2. Now I don't expect us at this point in our math careers to have the quadratic formula memorized, because that was from last year. But we still need to know how to use it. So we can Google it if we need to, and then use it. All right, negative b plus or minus the square root of b squared minus 4ac over 2a. Well, the b value is negative 3 here. The a value is going to be positive 2. And the c value is negative 7. If I plug all those values in and simplify, I will get my result. All right, so I end up getting something that looks like 3 plus or minus square root of 9 plus 56 over 4. So if I were to simplify this equation, I get x equals 3 plus or minus square root of 65 over 4. That seems to be kind of as far as I can go with that. So if I asked you to identify my zeros for this equation, my zeros are 3 minus square root of 65 over 4, comma 1, comma 3 plus square root of 65 over 4. Those are my exact answers. Decimals do not count. You can turn that into a decimal and verify that you did it correctly from your graph, but I need exact answers only on these types of problems. Otherwise, you won't get credit for it. Anybody can go into Desmos and find the decimal approximation. Finding that exact answer is the key here. All right, so find those exact answers for me. So don't leave a decimal ever. Leave it as a fraction if you can. Leave it as in this case, it's a radical and a fraction. So you'll need to leave your answers like that in these types of problems. Okay. Sorry, it was kind of a long stretch today, but I just had to do those 3 examples, show you what we're up to. And now I've got some practice problems for you guys to try. So problem 1 says this is a factor. Problem 2 says here's a 0. Problem 3 gives you a solution and it says find the zeros. And problem 4 is a real world practice problem. All right. So find the expression of depth. All right. So try those 4 problems. I'll put the answers up shortly, but go and work through those 4. We'll probably need about 10 minutes on these, maybe a little more. We'll do 15.